All right, so what we saw was the following. If you have a magnetic field in a region, one way to detect that is throw a charged particle. And if a charged particle is moving, it'll feel a force, okay? If the magnetic field was zero, it wouldn't feel any force, okay? No magnetic force. So a moving charged particle in the presence of a magnetic field feels a force. So it stands to reason if there is a current in the wire, current is a bunch of moving charges. So if there is a current in the wire and the wire happens to be in a magnetic field, it will feel a force. So this is a horseshoe magnet. There's the North Pole, there's the South Pole. The blue lines are the magnetic field lines. And here's a current. So here's a side view of this. And you can see that the magnetic fields are represented by crosses, so meaning the magnetic field is into the plane of the paper. And right now this wire is not carrying a current, so there are no moving charges and it's not feeling a force. Now, as soon as you pass a current like that, so a current in that direction. Okay, so these are the magnetic fields. So a current in that direction you can think of as positive charges moving in this direction. Okay. And B is into the paper. So if you, okay, so let's see. So if you see, V is pointing up and magnetic field is pointing into the sheet of paper. So if I turn from V to B, the force will be in that direction. Okay. So I don't know if you saw that clearly, but if positive charge is moving in this direction and the magnetic field is into the plane of the paper, the force will be in that direction. Okay. And that's what this thing is showing you. So if you have a current moving in that direction, there's a force on the part of the wire that's in the magnetic field, and the force is in this direction, and the wire bent that way. On the other hand, if you pass the current in this direction, the force will be in that direction. Okay, so what we are seeing is if you have a current carrying conductor in the presence of a magnetic field, it'll feel a force. Okay. And so this is extremely important for you to understand. You know that 90% of the work in the world is done by electric motors. And this is the basis for an electric motor. And you will see that. Okay. So the force on a current carrying conductor in the presence of a magnetic field is that idea is what's incorporated in a electric motor. Okay, so what this equation is showing you is this is the force on an individual charge, and then there's a whole bunch of charges in a current carrying conductor. So N is the density of free charges, and this is the volume of the wire in which the charges. So this is the number of charges. Okay. Anyway, all that can be simplified into the magnetic force on a current carrying conductor is I L cross B. The vector L is pointing, L is the length of the wire, and the vector direction of that is the direction in which the current flows. So here the magnetic field, and here the wire carrying a current, and this would be the vector L. Okay. And let's do another one. So again, there's the magnetic field, and if the current is flowing in this way, there is the vector L. So Okay, so the vector L points in the direction of the current. Okay. And it's the length of the wire that is in the magnetic field. Okay. So that's what that equation tells you. Okay, so the force, the magnetic force on a current carrying wire is I/L cross B. All right, so now we're working toward an electric motor over several slides. Okay, so now imagine here's a uniform magnetic field. That's what the blue line indicates. Somebody has a question. Okay. One second. It should become clear. So here's a bent piece of wire in a uniform magnetic field. We'll keep things simple. The field is, we'll keep the magnetic field uniform. Okay, so now here's this bent wire. What we'll do is to calculate the force on this wire, break it up into little pieces. We know how to calculate the force due to a straight piece of wire, which was that equation. Okay, so if you have a bent piece of wire, break it up into little pieces, and each little piece is a straight piece. So the force on this little piece, the dF, the force on that little piece is the current in the wire times ds cross B. Okay, and ds cross B. So if you turn a screw from here to there, it will come out of the paper. So it'll be perpendicular to the paper, coming out of the paper. So the force on this piece is coming out of the paper and perpendicular to the sheet. Okay, so to mimic that drawing, there is the magnetic field. Okay, so uniform magnetic field, and there is the current. The force on this little piece, ds, is the force is coming out of the paper. So that will be the force. And the dot indicating that you're looking at the arrow. So the force is coming out of the paper. Yeah. Now we want to find the force on the entire wire. Okay. So you just add up all these forces, the forces on each little piece. And that, of course, is an integral. Okay, so it's this integral. So you have to take the cross product and integrate over that. Now, if the magnetic field is uniform, that comes out. And then it's just the sum of all those little pieces, the sum of all those little pieces. Okay, all those purple arrows. And you know how to add vectors. And if you add all those vectors, what you get is this vector. Okay. So the force on this wire is the same as the force as if it were a straight wire like this with the same endpoints. Okay, so that's what this equation is telling you. The force on this bent wire is the same as if as the force would be on this straight wire carrying the same current. All right, so the next obvious thing is then if you had a loop, the forces from this starting point to the end point, if you had a loop, L prime would be 0, and the force on a loop, the net force on a loop is 0. So force on a closed loop in a uniform magnetic field is 0. The force is 0, but it turns out that the torque won't be 0. So the net force on a closed loop is 0. Okay. So let me make sure we understand this. So let's so let me show you a situation where all right, so here is the object, and let's say we apply a 10 Newton force, 10 Newton force here. See the net force on this guy is 0. However, the net torque is not 0. Okay, so this object will rotate about this point. So it'll rotate about that point, if about the center of mass. Okay. So the torque is not 0. Similarly, on a loop. Okay. So here is a loop of wire. It's in a uniform magnetic field, and from this equation, what you can tell is if L is parallel to B, if the current is parallel to B, then the force on that element is 0. Okay. So here's a uniform magnetic field, and here's a loop of wire carrying a current. This is anti-parallel to B, so the force on this guy is 0. The force on this guy is 0. And if you figure it out, so there is L, and B is in that direction. So if you turn from L to B, so if you turn a screw from here to there to the right, the screw would move into the plane of the paper. So the force on this guy is into the plane of the paper. And here is L. So if you turn a screw from here to there, it will move out of the plane of the paper. Okay. So it turns out that on this current loop of wire, the force on this current is into the paper, and into this, on this wire, it's out of the paper. And those two forces are equal and opposite. And so what they end up doing is they'll make this loop turn about that axis. Okay. So this magnetic field made the loop turn like so. Okay. So let me make sure you guys understand this. Okay. So here's the uniform magnetic field. Yeah. So let's. Okay, so the force on this guy is 0. The force on this guy is 0. The force on this guy is into the sheet. And the force on this guy is coming out of the sheet. And so the net result is this loop of wire will turn about that axis. Okay. So what we are saying is, as soon as you take a loop of wire, place it in a uniform magnetic field, and you pass a current through this loop of wire, and the magnetic forces make this loop turn. And that's what an electric motor does. You pass a current through an electric motor and something turns. This loop of wire turns in the electric motor. And you attach that to some external rotor, and that's how electric motors work. Okay, so this is the fundamentals of an electric motor. Okay, so the torque, again, so let's go back to there. So the torque will be here. So let's say this is the length of the wire. The torque will be this. This force will be counterclockwise torque, looking at it from the top, and the torque will be FL/2 plus this also is a counterclockwise torque, FL/2, and so F times L. Okay. Anyway, so what you can work out is, if you work out the details, where L is the length of that, L is B. Okay. So the force is, A is the length of this thing, IA times B is the force on each one of them, and B gives it the torque. Okay. So the torque on this loop it turns out is I, the current in this loop, A is the area of the loop times the magnetic field. And again, this is in a uniform magnetic field. So the torque is I times the area of the loop times the magnetic field. Okay. Again, let me summarize this. The net force on a closed loop in a uniform magnetic field is 0, but the torque is not 0. Okay. So again, just like in this simple example, the net force on this object is 0. There's a 10 Newton force in this direction, 10 Newton force in the opposite direction. The net force on this is 0, but you know that this guy won't remain at rest, he will rotate. So, which is different than this guy. In this case, the net force is 0 and the net torque is 0 as well. So, so in this case, the net force is 0 and the net torque is also 0. And this guy will neither move and neither accelerate nor rotate. This guy, the net force is 0, so his center of mass won't accelerate, but the net torque is not 0, so he will accelerate. He will have an angular acceleration. Okay, so just like that, this guy will rotate, and this is looking at the top, from the top, and he will rotate. Okay, no, this is looking from the bottom, and he will rotate clockwise. No, wait a second. So this force will into the sheet. Okay, it's so it's looking from the, oh no. Well, I guess this is not consistent. So if you look from the top, it'll rotate counterclockwise. If you look from the bottom, wait a second. You look from the top, it'll rotate counterclockwise. And you look from the bottom. Oh. Two, this is 2. So coming out, so you're looking from the bottom.
I think the illustration is correct because B is looking from the side, you know.
Yeah, no, yeah, B is from the side. So you're looking edge on, so you're looking from the bottom. The force is into the sheet. No, so this diagram is not right. Okay, so this is what was disorienting about it. So you're looking at from the bottom, but then this diagram is drawn top down. So you have to invert this, and that's why it's confusing. So this is not a good diagram. So you're looking at it from the bottom, but you're drawing as if you're looking from the top, and that's the problem. And then it'll go clockwise. So it's not a good diagram. Anyway, here's the important thing. So the force on this guy is into the sheet, this guy is out of the sheet, and he will rotate like that. If you look from the top, he'll rotate counterclockwise. Okay. This diagram is correct, but this is looking from the bottom, and then you flipped it, and it's rotating clockwise. Okay. All right. So here's the deal. So so if you have a loop in a constant magnetic field, again, the crucial thing is it's a constant magnetic field, and here's a loop of wire carrying a current. It feels a torque, and so it's convenient to define an area vector. Okay, so I is the current, the area vector is, okay, so here's what you do. You use your right hand, your fingers point in the direction of the current, okay, and your thumb points in the direction of the area vector. So now I know my right hand probably looks like my left hand for you guys on the camera, but anyway, so if your fingers point in the direction of the current, the thumb points in the direction of the area vector. So if your fingers point like that, there is the area vector. The magnitude of the area vector is just the area of this loop. This guy, I times area, is called the magnetic moment. So the torque is A cross B. Okay. So if you have a current carrying loop, okay, what happens is the torque makes the area vector turn towards the magnetic field. That's what it does. And now you see, if the current were zero, the torque would be zero. So if there's no current, this loop of wire would not turn. So an electric motor does not work if the current is zero. Okay. Now in an electric motor, of course, you pass a current and the loop turns towards the magnetic field. And once the area vector is lined up with that, then they switch the direction of the current. And so that the area vector points in the opposite direction and again, keeps turning in the same direction. Okay, so that's the trick in the electric motor. But anyway, if there is no current, there won't be any torque. So a current carrying conductor, a current carrying loop feels a torque in the magnetic field, okay? And so this area vector will turn towards the magnetic field, okay? And I'll show you a simulation in a second. Okay, so here we go. Let me show you the simulation. All right, so here's a view of the loop. This tells you the current is coming. So this is looking edge on. There's the magnetic field. Okay, so again, the loop is like so. Okay, and so and the current is flowing like that. The magnetic field is in this direction, and soon as I pass a current in this loop, it will turn like that. Okay, so there's the area vector, the force on this guy. So the current is coming out of on this side, it's coming out of the plane, and the current is going into the plane. And okay, so the force is in this direction. Okay, so let's start. And this loop of wire turns, feels a torque, and you see this guy is lining up with the magnetic field. And then he overshoots, okay? And this loop would oscillate. Okay. So in an electric motor, yeah, if you want it to keep turning, once the area vector lines up with that, then you switch the direction of the current, and so it'll keep rotating. Okay, and so that's what you do. Okay, so the current carrying loop feels a torque. Okay, and the torque is trying to line the moment associated with the loop with the direction of the magnetic field. All right, so we defined the magnetic moment. So what we're saying is a current carrying loop behaves like a magnet, and the magnetic moment is the strength of this magnet. So the magnetic moment of a current carrying loop is N, the number of turns in the loop, times the current times the area of the loop. Okay, so a current carrying conductor, loop of conductor, is an electromagnet. So this is what we mean by an electromagnet. The advantage of this magnet is you can turn it on and off. With an ordinary magnet, you can't turn it off. Okay, so that's the advantage of an electromagnet. And you can change the strength of the magnet as well. Yeah, you can have different number of windings, and for a given number of windings, you can change the current and you can change the strength of the magnet. All right, so there is the magnetic moment of a current carrying conductor, of a current carrying loop, and the torque it feels in the presence of a magnetic field is mu cross B. Okay. All right, so what this is showing you is in the following. So again, the blue lines are magnetic field lines, the magnetic field lines are in that direction. And you can figure this out for this loop. These are loops of wire, and we're looking at them edge on. There, the loop, the moment is lined up with the magnetic field, and this guy feels no torque. This guy will feel a torque. This guy, where the magnetic moment is perpendicular to the magnetic field, feels the greatest torque. Okay. All right. A magnetic moment in the presence of a magnetic field has potential energy, and the potential energy is defined as the torque is given by the cross product and the potential energy is given by the dot product. So the potential energy is defined minus mu dot B. Okay, so if you go to this one, mu is in this direction, B is in that direction. Right now it has a large potential energy. So it's like you holding a ball up at a certain height, and then you let go of the ball, the gravitational potential energy gets converted to kinetic energy. So that potential energy got converted to rotational kinetic energy. Okay. So, and when this thing lines up with the magnetic field, its potential energy is minimal. When when A is anti-parallel to B, then the potential energy is maximum. Okay. So again, now potential energy is being converted to rotational kinetic energy. Okay. All right, so that's, again, the torque on a loop carrying a current is mu cross B, and the potential energy is mu dot B. So the cross product gives you the torque and the dot product gives you the potential energy. All right, so these are not just of academic interest. So for instance, so let's say you have an object like this. Let's say this is a satellite and it's up in orbit and you want to turn the satellite. Okay, so right now it has zero angular momentum. If you can turn something in the satellite in this way, the satellite would, if you turn something in this way, the satellite would turn in the opposite direction. Okay. So you can place loops of wires like this in the satellite, and you can hit a computer key and turn on a current in this loop of wire. And there is the Earth's magnetic field, so this will work well for low Earth orbit satellites. And there's the Earth's magnetic field. Soon as you turn this current on, this loop of wire will turn toward the magnetic field, and the satellite will turn in the opposite direction. Okay, so by hitting a computer keystroke, you can make your satellite turn in various directions. Okay, so you would have 3 loops in mutually perpendicular directions, and you can turn the satellite any which way you want, okay, by a combination of those turns. So many satellites use coils called torquers to adjust their orientations. Torquers interact with Earth's magnetic field. They interact with the Earth's magnetic field. The advantage of such devices is that they use solar energy rather than thrust or fuel. You know, it costs money to put every gram in orbit. So the less weight you have to carry up to orbit, the more cost efficient it is. Okay, so if you can use thrusters or torquers for orientation changes, then you don't have to carry thruster fuel. Yeah. So again, like I said, this works well for lower orbit satellites. So here are typical values: magnetic moments, magnetic moment. So here is the magnetic moment. N is the number of loops, number of turns. I is the current, and A is the area of the, okay, so of the torquer. So if you have, so there are the typical values. The magnetic moment is 250 amp-meter square. Magnetic fields, so up there it's about 1/10 of the magnetic field on the surface of the Earth. And this is the kind of torque that is exerted on this loop. Yeah. 7 millinewton meter. Okay. You can also put gyros in spacecraft to turn. So again, if you turn the gyro in this direction, the satellite would turn in this direction. Okay. And as soon as you want to stop the turn, stop the gyro, and the satellite will it'll stop turning and it'll remain in that position. Okay. So that's how we. Yeah, and this can be also an electrically driven gyro. All right, so I will pause now. And give you guys a chance to ask questions.